Right now, inside every atom in your body, something impossible is happening. An electron is racing around a tiny nucleus, and the oldest laws of physics say it should crash into the center almost instantly. The whole atom should collapse in 16 trillionths of a second. Every atom in the universe should have died the moment it was born, so you should not be here at all. But you are. Tonight we chase down the strange reason electrons refuse to fall. We will shrink inside a cloud where the electron blurs across everywhere at once, watch a dead star hold itself up with the very same force, and find the single rule that gives all matter its size. If wonder like this keeps you awake, like and subscribe, then ride along with us. Take a breath. We begin. Hold out your hand and look at it. It feels solid. It looks solid. Every rule your senses know says it is packed tight, full of stuff. That is a lie your body tells you. Almost all of that hand is empty. Nothing. A vast, echoing void. Picture a single atom, the tiny building block that everything is made from. At its center sits the nucleus, a heavy little knot of matter. Around it, somewhere far away, spins an electron, and the gap between them is enormous. Here is a way to see it. Shrink yourself down and stand inside one atom. Put the nucleus at the center of a football field, a marble resting on the 50-yard line. Now go looking for the electron. You would have to walk all the way out of the stadium past the parking lot and drift somewhere across town before you found it. Everything in between is empty space. That is one atom. And you are made of about 7 billion of them. Stack all that emptiness together and the truth becomes strange. If you squeezed every atom in every human on Earth down and threw away the empty space, all 8 billion of us would fit inside a single sugar cube. One small cube, holding all of humanity. You have never touched anything in your life. Not really. When your hand presses a table, the outer electrons of your skin push against the outer electrons of the wood. They repel. They never meet. That tiny push is the only touch there is. So the world you live in is mostly nothing, held apart by invisible forces, and that raises a question that should keep you up tonight. If the atom is this empty, if the electron is drifting way out there while the nucleus sits alone at the center, what holds the whole thing together? What stops it from simply falling apart? The two are pulling on each other with real force. The nucleus carries a positive charge, the electron carries a negative one. Opposite charges attract, and they attract hard. It is the same kind of pull that snaps two magnets together across a gap. The closer they get, the harder that pull becomes. Every instinct says the electron should be yanked straight in. Down, down, into the center, until it slams into the nucleus and the empty space collapses. The stadium should crush to the size of the marble. It does not happen. The electron stays out there, keeping its distance year after year for billions of years in every atom that has ever existed. Something is holding the line, something we could not see. For a long time, nobody knew what. The greatest scientists on the planet stared at this puzzle and could not crack it. The math kept telling them the atom should die. Reality kept telling them it did not. The answer would turn out to be one of the strangest rules in all of nature. It rewrote what we thought was real. It explains why you can sit in your chair without falling through it, why stars burn, why you exist at all. But before anyone could find that answer, they first had to discover the tiny heart of the atom itself. And that discovery came by accident, from a man firing invisible bullets at a sheet of gold, waiting to see what would happen. The year is 1909. In a lab in England, a young scientist named Ernest Marsden is sitting in the dark staring at a faint glowing screen, doing what his boss told him to do. His boss is Ernest Rutherford, and Rutherford expects this experiment to be boring. The plan is simple. Take a thin sheet of gold, hammered so flat it is only a few hundred atoms thick. Then fire tiny invisible bullets at it. These bullets are called alpha particles, heavy little specks that shoot out of radioactive material at huge speed. Everyone already had a picture of the atom back then. They called it the plum pudding. The idea was that an atom was a soft blob of positive charge with tiny electrons scattered through it, like raisins stuck in a mushy dessert. Soft, spread out, weak. If that picture were true, the heavy alpha bullets should punch straight through the gold like a rock through fog. Maybe they would tilt a tiny bit. Nothing more. That is what Rutherford expected. That is what everyone expected. So Marsden watched. Each time a bullet hit the glowing screen, it made a tiny flash. Most of them flew straight through, exactly as promised. The experiment was working. It was dull. Then Rutherford asked Marsden to check something strange. Look behind the foil. See if any bullets bounce backward. Nothing should bounce backward. That would be insane. It would be like firing a cannon at a sheet of wet tissue paper and watching the cannonball come flying back at your face. Marsden looked, and there they were. Flashes. Some of the alpha bullets were hitting the gold and rebounding straight back the way they came. Rare, maybe one in every 8,000, but real. Rutherford was stunned. He later said it was the most unbelievable thing that ever happened to him in his life. Something inside that soft, mushy, spread-out atom was solid enough to slap a fast bullet backward. He worked through the math and reached one conclusion. The atom is mostly empty, just as the emptiness in your hand suggested. But hidden at its centre is something small and unbelievably dense. A tiny core packed with almost all the mass and all the positive charge, crammed into a space far smaller than the atom itself. He called this core the nucleus. To picture how small it is against the whole atom, remember the football field. The atom is the entire stadium. The nucleus is the single marble at the centre. Almost everything about the atom is empty, and its whole weight hides in that one dense speck. This was a triumph. Rutherford had found the heart of matter itself, the thing every atom is built around. His name went down in history. The discovery still stands today, confirmed 1,000 times over. But triumphs in science have a habit of hiding traps. The moment Rutherford placed that dense nucleus at the centre, with electrons circling far outside it, he broke his own picture of reality. Because now the electrons had to move. They had to circle that nucleus the way Earth circles the Sun, or the pull between them would drag them straight in. And the instant physicists worked out what a circling electron must do, a horrifying problem appeared. By every law they trusted, that electron was doomed. Every atom in the universe should have destroyed itself in a flash. So the atom now looks like a tiny solar system. A dense nucleus sits at the centre, like the sun. The electron whips around it in a circle, like a planet. Clean, simple, beautiful, and completely broken. The problem lives in one fact about electric charge, a fact scientists had known and trusted for decades. When you take a charged thing and force it to change direction, it throws off energy. It glows, in a sense. It bleeds power out into the space around it as invisible waves. An electron circling a nucleus is changing direction every single instant. To move in a circle, you cannot travel in a straight line. You have to keep turning, keep curving inward, over and over, forever. So the electron is constantly changing direction, which means it is constantly bleeding energy away. Think about swinging a ball on a string over your head. To keep it going in a circle, you have to keep pulling it inward toward your hand. The electron feels that same inward pull from the nucleus, and it obeys it by curving. But every curve costs energy. Here is why that is a death sentence. The energy holding the electron in its wide orbit is the only thing keeping it far from the nucleus. As that energy drains away, the electron cannot hold its distance. It sinks a little closer, and the closer it gets, the faster it whirls, and the faster it whirls, the more energy it throws off, which pulls it closer still. It is a spiral of doom. Each loop tighter than the last, each loop faster than the last. The electron races inward, tighter and tighter, spinning like water screaming down a drain until it smashes into the nucleus and the atom ceases to exist. This is the trap Rutherford walked into. The very model that won him glory, the tiny solar system, carried its own destruction inside it. Under the old laws of physics, an atom could not survive. It would eat itself alive in an instant. This error ran deep. The physics that predicted the collapse was the same physics that built bridges, ran engines, and lit cities. It was tested. It was trusted. It worked everywhere else in the world. Nobody had any reason to think it would fail inside the atom. Yet if it were right, nothing around you could exist. The chair, the air, your own beating heart, all of it is made of atoms. If atoms truly collapsed the way the math demanded, none of this would be here. The universe would be a thin soup of crushed matter and nothing else. Scientists stared at this and felt the ground shift under them. They had two facts, and both looked solid, and they could not both be true. Fact 1. The laws of electricity say the circling electron must spiral in and die. Fact 2. Atoms are everywhere, stable, lasting for billions of years without collapsing. One of those had to break. Either the atom was not a little solar system after all, or the laws they had trusted for a century were hiding a crack so deep it would shatter their whole idea of reality. They did not yet know which. But they could at least ask a sharper question. If the atom really is doomed, exactly how fast should it die? The answer, when they calculated it, was so short it barely counts as time at all. So the physicists did the math. They took the doomed electron spiraling inward, bleeding energy with every turn, and they asked the cold question. Start the clock the moment the atom forms. How long until the electron hits the centre and the whole thing dies? The answer came back, and it was brutal. About 16 trillionths of a second. That number is almost impossible to feel, so let us stretch it out. A trillionth of a second is to 1 second what 1 second is to about 32,000 years. The electron's entire death spiral, from wide orbit to fatal crash, would be over faster than the fastest camera on Earth could ever hope to catch it. To put it another way, in the time it takes you to blink once, an atom built the old way would be born and die more than 20 million times over. Blink, 20 million lifetimes of matter, gone. Every atom in your body, every atom in this room, every atom in the sun and the oceans and the farthest star. All of it, according to the trusted laws of physics, should have flickered out of existence almost the instant it appeared. Sit with how strange this is. The universe is about 14 billion years old. Atoms are supposed to last a heartbeat of a heartbeat of a heartbeat, then vanish. Instead, they have survived, unbroken, for billions upon billions of years. The gap between the prediction and the truth was staggering. It stretched from a fraction of a second all the way to forever. When a prediction misses reality by that much, one of two things is happening. Either the scientists made a silly mistake in their sums, or something is deeply, wildly wrong with the rules themselves. They check the sums, then they check them again. The best minds in Europe went over every step. The math was clean. Following the laws of electricity that everyone trusted, the answer really was that short. There was no arithmetic error to hide behind, which left the terrifying option. The laws themselves, the proud physics that had ruled science for 200 years, had to be broken somewhere deep inside the atom. Some new rule, something nobody had ever seen, was reaching in and stopping the collapse. That rule was invisible. It left no obvious fingerprints. It simply held the electron out there, at its safe distance, refusing to let it fall, in defiance of everything the textbook said. Whatever it was, it had to be powerful. It had to be everywhere, in every atom, working without fail, without rest, for the entire life of the universe. If it ever slipped, even once, that atom would collapse in a flash and take its little piece of the world with it. Something was standing guard inside all matter, silent and unseen, and nobody, not one scientist alive, could say what it was or where it came from. To find it, they first had to understand exactly why the electron was bleeding energy in the first place. Why does a curving charge have to throw off power at all? Answer that, and you start to see the shape of the mystery. The reason turns out to connect the electron in your fingertip to the radio signal in your phone in a way that sounds impossible until you see it. To understand why the electron was doomed, you have to understand your phone. Every time you send a text, your phone shakes electrons back and forth inside a tiny antenna. Push them one way, pull them back, over and over, millions of times a second. And every time those electrons change direction, they do something remarkable. They send out a ripple into the space around them. That ripple is a radio wave. It races off at the speed of light, carries your message to a tower miles away, and eventually reaches someone else's phone. The whole invisible web of texts and calls and videos flying through the air is built on one simple trick. Shake a charge, and it throws off waves. This is a rock-solid rule of nature, tested countless times, running every wireless device on Earth right now, A charge that speeds up, slows down, or turns will always bleed some of its energy away as waves. Always. Now look back at the electron in the atom. It is a charge, and it is turning constantly, endlessly, as it circles the nucleus. By the exact same rule that carries your text message, that circling electron must be throwing off waves too. The electron is acting like the tiniest radio antenna in the universe, broadcasting energy it cannot afford to lose, every fraction of every second, whether it wants to or not. And here is the cruel part. Your phone has a battery. When its antenna radiates energy away, the battery quietly refills it. The shaking continues because something keeps paying the bill. The electron has no battery. Nothing refills it. Every wave it throws off is energy gone for good, stolen from the only bank account it has, the energy of its own orbit. It is spending itself into bankruptcy, and no one is topping it up. So the electron falls. As its orbit energy drains into radio waves, it can no longer hold its wide circle. It drops inward, and an electron in a tighter orbit has to move faster and turn harder, which makes it radiate even more fiercely, which drains it even faster. Picture a satellite in orbit that scrapes the very top of the atmosphere. The faint drag steals a little speed. Losing speed, it drops to a lower orbit where the air is thicker and the drag is stronger, so it slows even more and drops again. Round and round, faster and lower, until it burns in a final screaming plunge. The circling electron faces the same fate, only far quicker and far more violent. This is what set that death clock ticking. This is the engine behind the whole disaster. The electron cannot circle without radiating, and it cannot radiate without falling, and it cannot fall without radiating harder still. Every attempt to save the little solar system ran into this wall. As long as the electron moved in a normal orbit, the laws of radiation would drain it dry and drop it into the nucleus. The model was beautiful and it was fatal. So one brave physicist decided to do something almost unthinkable. If the trusted laws demanded the atom destroy itself, and yet atoms plainly survived, then maybe, inside the atom, those trusted laws simply did not apply. Maybe there were secret orbits where the electron was somehow forbidden to radiate at all. It sounded like cheating. It sounded like magic. And it was about to work. Let us play out the nightmare. Suppose the old physics had its way. Suppose every electron really did spiral in and crash. What kind of universe would that leave behind? Start with the atom itself. Once the electron falls into the nucleus, the atom loses its outer shell completely. And that outer shell is everything. It is the part of the atom that reaches out and grabs onto other atoms. It is how atoms hold hands. Kill the electron orbits and atoms can no longer join up. No joining means no molecules, no water, which is 2 hydrogen atoms clasped to 1 oxygen, no air, no salt, no sugar, no rock. The entire idea of chemistry, of atoms bonding into new things, would simply be gone. Without chemistry, there is no biology. Your body is a vast humming machine of molecules, proteins folding, cells dividing, blood carrying oxygen. Every bit of that is atoms bonded to atoms in careful patterns. Collapse the atoms and the machine has no parts to build from. No cells, no life, no you. Now look up at the sky. Stars shine because their cores squeeze atoms together and release energy. But a collapsed atom, with its electron already crushed inside, cannot burn that way. The furnaces of the stars would never light. The sky would be black and cold, with no sun to warm a single world. And it gets worse. The matter that was left would be horrifying stuff. All those tiny nuclei, stripped of their electron clouds, would be free to pack together with nothing holding them apart. Remember, the electron cloud is what gives an atom its size. Take it away, and you take away the space. Matter would crush down to the density of a nucleus, the same insane density that made Rutherford's bullets bounce. A single spoonful of that stuff would weigh as much as a mountain. The whole universe would be nothing but a thin scatter of that crushed matter. Silent, dark, and dead. No planets, no people, no light, no chemistry to build anything. Ever. That is the universe the old laws promised. A graveyard that formed and died in the same instant, with no one ever there to see it. And yet, look around. Here you are, warm, alive, breathing, thinking, listening to this. The stars are burning, water flows, your heart is beating out its steady rhythm right now. The graveyard universe did not happen. Somehow, matter dodged its own death sentence. This sits at the very heart of the mystery. The most trusted physics of its day said clearly, without hesitation, that you cannot exist. The math was checked, the logic was sound, the conclusion was airtight, and the conclusion was wrong. Your existence is the loudest proof in the world that the old rules were missing something enormous. Every breath you take is evidence of a hidden law strong enough to overrule the entire physics of its time. So the real challenge landed in the lap of a young Danish scientist. Everyone could see the atom refuse to collapse. Nobody could say why. He decided to stop asking why the electron fell and start asking a stranger question instead. What if the electron was only allowed to live in certain special orbits, and forbidden from all the rest? It was a wild guess, and it cracked the door open. His name was Niels Bohr, and in 1913 he was young, stubborn, and willing to break the rules everyone else worshipped. Bohr looked at the doomed atom and made a decision that shocked older scientists. He decided to simply declare that the electron could not spiral inward. He would build the survival of the atom into the rules by hand. Here was his bold idea. The electron may orbit only at a few special distances, like a set of fixed steps on a staircase. It can stand on any step. It can never stand between them. Think of a ladder. You can put your foot on the first rung or the second or the third. You cannot rest your foot in the empty air halfway between two rungs. There is no place to stand there. Bohr said the atom works the same way. The allowed orbits are the rungs. The spaces between are simply off limits, forbidden, impossible. And on the lowest rung something special happens. When the electron sits on the bottom step closest to the nucleus, it is stuck. There is no lower step to fall to. The staircase ends. So the electron just stays there, circling forever, unable to spiral in because there is nowhere left to go. This one move saved the atom. If the electron cannot drop below the bottom rung, it can never crash into the nucleus. The death spiral is blocked. The clock that promised destruction never even starts. The atom lives. And Bohr's idea did something even better than survive. It made predictions. When an electron jumps from a higher rung down to a lower one, it dumps the leftover energy as a flash of light. Bohr's staircase said those flashes should come only in certain exact colours, matching the exact size of the jumps. Scientists had been staring at those exact colours for years. When you heat up hydrogen gas, it glows, and if you split that glow through a prism, you get a set of sharp coloured lines, always in the same places. Nobody knew why. Bohr's ladder predicted them almost perfectly. The math lined up with the real colours of real glowing atoms. It was a stunning success. A young man had reached into the atom, declared a brand new rule out of thin air, and reality had agreed with him. Bohr won a Nobel Prize. His model went into every textbook. For a while, it looked like the mystery was solved. But if you were paying close attention, a question was clawing at the back of your mind. It is the same question that should be bothering you right now. Why? Why should the orbits come in a staircase at all? Why these rungs and not others? Why is the electron forbidden from the spaces in between? Bohr had a rule that worked, and worked beautifully, yet he could not say where the rule came from. He had written the answer without understanding the reason. It was as if someone handed you a locked safe, and the exact combination that opens it, but refused to explain how they knew the numbers. The safe opens, the combination is correct, and you still have no idea why those numbers, of all numbers, are the ones that work. That gap, that missing why, would haunt physics for the next decade, and the person who finally filled it started with an idea so strange that people thought he was joking. Bohr's ladder had a secret it did not want to share. It worked, but only just, and only in one place. Push it even slightly and the whole thing began to buckle. The model handled hydrogen beautifully. Hydrogen is the simplest atom there is, one lone electron circling one lone proton. For that clean little system, Bohr's staircase nailed the glowing colours almost perfectly. Scientists cheered. Then they tried it on the next atom up, helium, which has 2 electrons instead of 1. The model stumbled. The predictions drifted off the real numbers. Try a heavier atom, with more electrons still, and Bohr's neat ladder fell apart completely. The colours it predicted were wrong. The magic only worked for the one simplest case in all of nature. That was the first crack. A true law of the universe should work everywhere, on every atom from the lightest to the heaviest. A rule that fits only hydrogen is a lucky guess wearing the costume of a law. There was a deeper problem too. Look closely at those glowing hydrogen colours with a better instrument, and each sharp line splits into several finer lines huddled close together. Bohr's model had no idea these extra lines existed. It could not explain them. They simply should not have been there, according to his staircase, yet there they sat, plain as day. Every patch someone tried to add just made things messier. Scientists bolted on extra rules, tilted the orbits, spun them at angles, piling fixes on top of fixes to force the model to match reality. It started to look less like a clean truth, and more like a machine held together with tape and string. And underneath it all sat that unanswered question from before, the one Bohr could never escape. He had declared that only certain orbits were allowed, but he had no reason for it. He pulled the rule out of the air because it saved the atom, and for no other cause. In science, an answer with no reason behind it is a loan you will eventually have to repay. Bohr himself knew this. He was honest about it. He knew his model was a stepping stone, a clever trick that pointed towards some deeper truth still hidden from view. Something real had to be underneath the staircase, something that would explain why those special orbits existed and no others. He just could not see what it was. So physics was stuck in a strange place. It had a rule that half worked, that saved the atom and predicted hydrogen, yet failed on everything harder and rested on no foundation at all. The mystery was covered, but it was covered by a sheet, and everyone could see the shape of the monster still moving underneath. The breakthrough, when it finally came, would arrive from a direction nobody was watching. It came from a French prince of all people, a man from a noble family who had wandered into physics almost by accident. He asked a question so odd it sounded like nonsense. Everyone knew the electron was a particle, a tiny solid speck of matter. But this prince wondered something else entirely. What if that was only half the story? What if the electron, this speck we imagined as a marble, was actually spread out and rippling, behaving like a wave rolling across the sea? It sounded absurd. It was about to explain everything. The prince was named Louis de Broglie, and in 1924 he wrote a short piece of work so daring his own teachers were unsure what to do with it. For years, scientists had been wrestling with the light. Light was supposed to be a wave, a ripple spreading through space. Yet experiments kept showing it also behaved like a stream of tiny particles, little packets of energy. Light seemed to be both at once, a wave and a particle, depending on how you looked at it. This was already deeply weird. De Broglie stared at that weirdness and had a thought that flipped it inside out. If light, which everyone called a wave, could act like a particle, then maybe the electron, which everyone called a particle, could act like a wave. Maybe the strangeness ran both ways. It sounds like a small idea. It was an earthquake under the whole of physics. Picture the electron the old way, as a tiny hard marble, whizzing around the nucleus. De Broglie said to erase that picture. Imagine the electron smeared out, spread around the atom as a wave, like a ripple wrapped into a ring around the centre. It hums all the way around its orbit at once, everywhere along the circle. Every moving thing, de Broglie claimed, has a wavelength, a size to its ripple. A baseball has one too, and so do you when you walk. But for big, heavy things, the wavelength is so unbelievably tiny that you could never notice it in a billion years. For something as light as an electron, though, the wavelength is huge compared to the atom. So huge that the wave nature takes over completely. This was a bold claim with no proof behind it yet. It could have been pure fantasy. So people tested it. They fired electrons at a crystal, the way you might shine light through a fine grating, and they watched what came out the other side. What they saw settled it. The electrons spread out and made a pattern of ripples, bright rings, and dark rings, the exact kind of pattern that only waves can make. Solid little particles could never do that. The electron truly was rippling. De Broglie was right, and he earned a Nobel Prize for a hunch that sounded like a joke. So now the atom looked completely different. The electron was a wave wrapped around the nucleus, and the instant you picture it that way, something clicks into place, something that had been missing for over 10 years. Remember Bohr's mysterious staircase, the special orbits with no reason behind them? De Broglie's wave was about to hand over that reason. If the electron is a ripple looped into a ring, then only certain rings will work. A wave has to meet itself cleanly as it comes back around, or it cancels itself out and dies. That single rule, a wave fitting neatly around a circle, would finally explain Bohr's forbidden orbits. The staircase had a real cause at last. It came straight out of the shape of the electron's own wave, hidden there the whole time, and to see exactly how that works, you only need to think about something you have heard 1,000 times without ever knowing it held the secret of the atom. A guitar string, plucked, ringing out a single clear note. Pick up a guitar and pluck a string. It sings one clear note. Pluck it again, and you get the same note every time. The string seems to know which sound it is allowed to make. Here is why. When you pluck the string, a wave runs up and down it. But the string is tied down hard at both ends, so the wave gets trapped, bouncing back and forth. When the bouncing settles, the string falls into a smooth, steady shape that just sits there humming. Scientists call this a standing wave. The trick is that only certain shapes fit. The string is pinned at both ends, so whatever wave forms on it has to start and end at those fixed points. A wave with one smooth hump fits. A wave with 2 humps fits. A wave with 3 humps fits. Anything in between, a wave with 2.5 humps will not fit, because the loose end would have nowhere to attach. That leftover wave cancels itself out and vanishes, so the string can only ring at certain special sizes of wave, and each size makes a certain note. That is why a guitar plays clean, separate notes instead of a smeared mush of sound. The fixed ends allow some waves and forbid all the rest. Now bend that string into a circle and wrap it around the nucleus. This is exactly what de Broglie's electron does. The electron wave has to loop all the way around the atom and come back to where it started. And here is the rule that changes everything. The wave has to meet itself smoothly. The crest that comes around has to line up with the crest it started as, wave matching wave, perfectly. If the wave fits a whole number of times around the circle, one full loop or 2 or 3, it lines up with itself and survives. It becomes a standing wave wrapped in a ring, humming steadily, going nowhere. That is a stable orbit. But if the wave does not fit evenly, if it goes around 2.5 times, then the crest comes back and lands on a trough. The wave crashes into itself, it cancels out and dies. That orbit simply cannot exist. Look at what just happened. The allowed orbits are the ones where the electron wave fits a whole number of times around the ring. All the others are forbidden. That is Bohr's mysterious staircase, appearing all on its own, straight out of the simple fact that a wave has to meet itself. The rungs of the ladder are the whole number waves, 1 loop, 2 loops, 3. The forbidden gaps between them are the sizes where the wave would cancel itself out. Bohr had guessed the steps were there. De Broglie and the guitar string revealed why. For over 10 years, physics had been carrying a rule it could not explain. Now the reason was sitting right there in a plucked string. The electron survives only where its own wave can survive, wrapped clean around the ring, meeting itself without a single stumble. This was a huge leap forward. The forbidden orbits had a cause. The atom made sense in a way it never had before, but de Broglie's beautiful wave carried a hidden danger, one nobody noticed at first. Because if the electron is truly a wave, a ripple with a real size, then it cannot go just anywhere. A wave needs room, and there is one place in the whole atom with almost no room at all. One place where a big rolling wave simply cannot fit, the very center, the nucleus itself. Think again about that guitar string bent into a ring around the nucleus. The wave loops around the outside, 1 clean hump or 2 or 3 humming steadily. Out there in the wide orbit, the wave has plenty of space to stretch and roll. Now try to drag that wave inward, toward the center, and watch what goes wrong. The electron's wave is big. Compared to the tiny nucleus, it is enormous, like an ocean swell trying to squeeze into a teacup. As you push the wave closer to the center, the circle it has to wrap around gets smaller and smaller, the room shrinks, and the wave has to cram itself into that shrinking space. A wave hates being crammed. To fit inside a tiny circle, it has to bunch up its ripples tighter and tighter, packing more waves into less room. Picture folding a long bedsheet down to fit inside a matchbox. You can fold once, twice, a few times, but soon the sheet fights you, bunched and straining and refusing to go smaller. The electron wave fights back the same way, and here is the strange thing that fighting means. In the world of waves, squeezing a wave into a smaller space forces it to carry more energy. A tightly bunched wave is a wildly energetic one. So the closer you try to push the electron toward the nucleus, the more its energy blows up faster and faster, screaming upward. To fall all the way into the center, the electron would need its energy to climb towards something impossibly high. The wave would have to bunch down to almost nothing, and its energy would rocket toward the sky. Nature will not pay that price. There is a floor the electron cannot drop below, a smallest circle its wave can bear to fit. So the wave stops. It holds at a certain size, spread comfortably around the nucleus, refusing to collapse inward, because collapsing would cost far more energy than it could ever gather. The center stays empty. The atom stays open. The death spiral is blocked, not by a rule Bohr wrote down by hand, but by the plain nature of what the electron actually is. This is the beginning of the real answer. The electron cannot fall into the nucleus because it is a wave, and a wave cannot be squeezed to nothing without its energy exploding. The atom has a size for the same reason a plucked string has a lowest note. Some things simply refuse to be crushed smaller. It is a gorgeous picture, and it is almost right. But there is a puzzle still buried inside it. Why does squeezing a wave force its energy to explode? Where does that violent resisting energy actually come from? Answer that, and you reach the deepest flaw of the whole mystery. The man who found that flaw was 25 years old, and he stumbled onto a rule so strange it seemed to say the universe itself will not let you know everything at once. His name was Werner Heisenberg, and in 1927 he wrote down an idea that unsettled even the scientists who believed it. People still argue about what it truly means, but its effect on the atom is beyond doubt. Heisenberg discovered a hard limit built into nature. It says you can never know two things about a tiny particle at the same time with perfect sharpness. The two things are where it is and how it is moving. Pin down exactly where an electron is, and its motion becomes a blur. Pin down exactly how it is moving, and its position smears out into a fog. Squeeze one down tight, and the other explodes outward. You can never trap both. Nature will not allow it. This is not about weak instruments or clumsy scientists. It is a law woven into the fabric of reality. The universe simply does not hold both facts in sharp form at once. The tinier the world you look at, the more this fog takes over. Let us make it real with a comparison. Imagine trying to photograph a hummingbird's wings. If you use a superfast shutter, you freeze the wing in one crisp spot, but the photo cannot show you how fast it was beating. If you use a slow shutter to capture the speed, the wing smears into a blur and you lose its exact place. You can have a sharp position or a sharp motion. You cannot have both in the same picture. Heisenberg said the whole universe works like that camera, all the way down. Now bring this back to the electron trying to fall into the nucleus. To crash into the center, the electron would have to be pinned right there, in that impossibly tiny spot at the heart of the atom. Its position would be nailed down to almost a single point. But Heisenberg's rule says the moment you nail down position that tightly, the motion goes wild. The more precisely you know where the electron is, the more violently and unpredictably it must be moving. So the electron cannot simply sit still at the center. Trapping it in that tiny space would force it to have a huge, frantic, thrashing motion. And a wildly moving electron has enormous energy. That frantic energy would immediately fling it back out, away from the center, refusing to be held. This is the reason underneath the reason. This is why squeezing the electron's wave made its energy explode earlier. It was Heisenberg's rule the whole time. Confine the electron to a smaller space, and its motion, and therefore its energy, must blow up to match. The wave was showing the same law from a different angle. The nucleus wants to pull the electron in and trap it in a point. Heisenberg's rule forbids that trapping. The tighter the trap, the harder the electron fights to escape it. The center of the atom is the one place the electron can never be caught. So the atom stays open because reality itself refuses to let the electron be pinned down. That is the true guard standing inside all matter. And it turns out this guard fights back with a strength that grows more violent the harder you press. Try to squeeze an electron into a corner and it does not shrink quietly. It rages. To feel how strange this rule is, imagine you could grab a single electron and try to trap it. Not just push it a little. Actually cage it, force it into a smaller and smaller box, and see what happens. At first it seems easy. You build a little box and drop the electron inside. But the instant you shrink that box, the electron changes. It starts to move faster. Not because you pushed it, not because anything hit it. It speeds up all on its own, simply because you took away its room. Shrink the box again, and it moves faster still. Shrink it more, and the electron becomes a frantic thrashing thing, hammering against the walls of its cage with more and more energy. The smaller the prison, the wilder the prisoner. It is as if the electron despises being confined and lashes out harder the tighter you squeeze. This is Heisenberg's rule turned into raw force. A trapped particle carries motion, and a tightly trapped particle carries violent motion. Confinement itself creates energy out of the electron, energy that grows without limit as the space shrinks toward a point. Here is a number to feel the scale of it. If you tried to squeeze an electron down into a space the size of the nucleus, the tiny center of the atom, the energy it would fight back with would be staggering. It would thrash so violently that no ordinary pull could ever hold it there. The nucleus simply is not strong enough to cage that fury. Think of it like a coiled spring. A loose spring sitting on a table holds no push, but press it down, compress it into a tight little coil, and you can feel it straining against your hand, desperate to fling back open. The harder you compress it, the harder it shoves back. The electron is a spring like that, except its push comes from the deepest law of the small world, and it grows far more fiercely than any metal ever could. So the electron in an atom lives in a standoff. The nucleus pulls it inward, trying to force it into a smaller and smaller space near the center. But every step inward shrinks the electron's room, and shrinking its room cranks up its thrashing energy, which shoves it right back out. The pull inward wakes up a violence that pushes outward. This is why matter takes up space at all. This is why you cannot squeeze a solid down to nothing. Push atoms together, force their electrons into tighter room, and those electrons fight back with a rising energy that resists the squeeze. That resistance is the firmness of every solid thing you have ever leaned on. Press your palm flat against a wall right now. The wall does not give. What you feel is countless electrons refusing to be pushed into smaller space, shoving back exactly the way that caged electron shoves against its shrinking box. The hardness of the wall is the fury of confined electrons made large enough to touch. So the atom holds two opposite forces in perfect balance. One drags the electron in, the other flings it out. Neither one wins outright, and the exact place where they meet, where the pull and the push cancel each other cold, decides something enormous. It decides how big every atom in the universe is allowed to be. Every atom is a battlefield and the war never ends. Two forces are locked against each other, pulling in opposite directions, and the whole existence of the atom depends on the fact that neither one can win. On one side stands the pull. The nucleus is positive, the electron is negative, and opposites attract. This pull reaches out and hauls the electron inward, always inward, trying to drag it down to the center and end the standoff. Left alone, this force would win in an instant and crush the atom flat. It is the same pull that started the death spiral in the first place. On the other side stands the push. This is the strange new force we just uncovered, the violence of confinement. The more the electron is squeezed toward the center, the more frantically it moves, and the harder it fights to fly back out. This push comes straight from Heisenberg's rule, and it grows stronger the closer the electron is pressed. Picture a tug of war, two teams hauling on a rope. On the left, the pull of the nucleus, dragging the electron toward the center. On the right, the push of confinement, shoving it back toward open space. The knot in the middle of the rope is the electron, and that knot settles wherever the two teams pull with exactly equal strength. Now here is the beautiful part. These two forces do not stay the same as the electron moves. They change, and they change in opposite ways. Bring the electron closer to the nucleus, and the pull gets stronger. Yes. But the push gets stronger too, and it climbs even faster, because the electron is being crammed into less room. Push past a certain point, and the outward shove overwhelms the inward pull, and the electron is thrown back out. Let the electron drift too far away, and the opposite happens. Out in the open, the push relaxes, the electron calms, its frantic energy fades. But now the pull of the nucleus, always reaching, wins the contest and hauls it back inward. So the electron cannot fall all the way in, because confinement flings it out, and it cannot drift all the way away, because attraction reels it back. It is trapped between two failures, squeezed from one side, pulled from the other, allowed to rest only in the narrow zone where the two forces meet as equals. That zone is not a single, razor-thin point. It is a comfortable region, a sweet spot where the electron can settle and hum, held in place by a truce between its two enemies. The pull and the push, forever cancelling, hold the electron at a steady distance year after year for the whole life of the universe. This is the real secret of why the atom survives. It is a balance, a standoff, a war with no winner, and that endless stalemate is what keeps the centre empty and the atom whole. Every atom in your body is holding this balance right now, silently, without rest. And that raises one last question, maybe the most amazing one of all. If the size of the atom is set by exactly where these two forces meet, then that meeting point is not random. It is fixed by the laws of nature themselves, which means every atom of a kind should come out the exact same size. And they do. Here is something you might never have stopped to wonder about. Why is an atom the size it is? Why not twice as big, or 1,000 times smaller? Why does hydrogen come out to one particular width, the same everywhere, in every corner of the universe? The answer is the truce line from earlier. The exact spot where the inward pull and the outward push cancel each other is not a matter of chance. It is fixed by the deep constants of nature, the fundamental numbers that never change, and that fixed spot sets the size of the atom. The pull follows a known law. The push follows Heisenberg's rule, also known. Set them equal, ask where they balance, and out pops a single distance. That distance is the natural size of the atom, and physics can calculate it from scratch, without ever measuring a real atom at all. When scientists first did this, the number that came out was astonishing. It matched the real size of the hydrogen atom almost perfectly. They had predicted the width of an atom using nothing but the balance of two forces, and reality agreed. This was one of the greatest triumphs in the history of science. The atom that results is unbelievably small. You could line up about 10 million hydrogen atoms across the width of a single grain of sand. Line them shoulder to shoulder, and it would take roughly 500,000 of them just to span the thickness of one sheet of paper. That tiny width is the truce line, made real, the frozen result of the endless war inside. And because the laws of nature are the same everywhere, that truce line is the same everywhere. A hydrogen atom in your body, a hydrogen atom in the sun, a hydrogen atom in a galaxy 10 billion miles beyond 10 billion miles away, all come out to the exact same size. The balance point does not care where you are. The forces are identical, so the answer is identical. Think about what that means. Every atom of a given kind is a perfect copy of every other. They are not roughly similar, like snowflakes or fingerprints. They are exactly the same size down to the finest measure, across the entire universe. The war inside each one settles at precisely the same line, always. This is why matter is so orderly. This is why chemistry works the same on Earth as it does on a distant star. The rules that set atomic size are woven into the universe itself, and they do not bend. Every brick in the cosmos is cut to the same measure by the same silent law. So the size of everything around you, the width of a wire, the thickness of your skin, the reach of a molecule, all of it traces back to this one balance point deep inside the atom. Change the forces even slightly, and every atom would swell or shrink, and the whole world would be built to a different scale, if it could exist at all. The electron then sits at its truce line and settles down into the lowest, calmest state it can find. It stops falling, it stops fighting, it rests, and that resting place has a special name and a special property, one that turns out to be the final lock on the door of the atom. It is the bottom floor of all existence, and once the electron reaches it, there is nowhere left in the entire universe for it to fall. Every atom has a basement, and it is the most important floor in all of nature. Scientists call it the ground state. It is the lowest place the electron can possibly go, the calmest, most settled spot in the whole atom. Think back to Bohr's staircase, the rungs the electron can stand on. The ground state is the very bottom rung. Below it, there are no more steps. There is no floor beneath the floor. The staircase simply stops. This is the final piece of the puzzle. When an electron in a higher orbit loses energy, it drops down a step and gives off a flash of light as it falls. It can keep dropping step by step, shedding light each time, but when it reaches the ground state, the falling stops for good. There is no lower rung to drop to. The electron has hit the bottom of everything, so it stays. It cannot spiral into the nucleus, because that would mean falling below the bottom rung, and no such place exists. The death spiral that terrified physicists for years is blocked by a simple fact. You cannot fall off the ground floor, there is nowhere lower to go, and this ground state is not empty of energy. Remember the standoff, the pull and the push balanced against each other. Even at the very bottom, that balance is still humming. The electron down there still carries motion, still holds a certain amount of energy, the smallest amount the atom allows. It is the least energy the electron can ever have, and it can never ever have less. Here is a comparison to hold on to. Imagine a ball rolling around inside a bowl. Let it lose energy, and it rolls lower and slower, spiraling down toward the bottom. In the ordinary world, it finally comes to rest, dead still, sitting motionless at the lowest point. That is what everyone expected the electron to do, roll down and stop dead in the center. The electron does not do that. When it reaches the bottom of its bowl, it does not sit still. It keeps a low, restless hum of energy, a motion it can never shed. Because sitting perfectly still at a single point is exactly what Heisenberg's rule forbids. The bottom of the atom's bowl is not a point of rest. It is a floor of permanent, gentle unrest. This changes how you should picture the atom entirely. The electron is not a marble parked at a spot. It is a spread out, humming presence, filling a region around the nucleus, always moving, never falling further, held at the lowest energy the universe permits. That is the true reason the electron never crashes. It has already fallen as far as falling can go. It reached the basement long ago and has been resting there ever since, in every atom for billions of years, unable to descend one step lower because the universe built no such step. And this leads to one of the strangest facts in all of physics. That leftover hum of energy at the bottom never goes away. You cannot cool it out. You cannot freeze it away. Chill the atom down as cold as anything can possibly get. Colder than deep space. Colder than any place in the universe. And the electron will still be humming with that same restless energy, refusing to go quiet. Cold is really just slowness. When you cool something down, you are asking its particles to move less, to slow their jittering, to calm down. The colder it gets, the slower everything moves. So it seems obvious that if you could cool something enough, everything would finally stop. Scientists even found the ultimate limit. There is a coldest possible temperature, a floor below which nothing can go. They call it absolute zero. It sits at about 460 degrees below zero on a Fahrenheit thermometer, far colder than the darkest gap between the stars. At absolute zero, all ordinary motion is supposed to freeze into perfect stillness, the end of all movement, except the electron never gets the message. Chill an atom all the way down to absolute zero, squeeze out every last drop of ordinary heat, and the electron inside is still moving, still humming, still carrying that low, restless energy at the bottom of its bowl. It refuses to stop even at the coldest temperature the universe allows. This leftover motion has a name. Scientists call it zero-point energy, the energy that remains when all other energy has been stripped away. It is the motion you cannot remove, the jitter that survives the deepest cold there is. Why does it survive? Because of the rule we have followed this whole time. For the electron to go perfectly still, it would have to sit at one exact spot with exactly zero motion. Heisenberg's rule flatly forbids that. You can never have a particle with a sharp position and no motion at once, so perfect stillness is impossible. Even at absolute zero, the electron must keep some motion, or it would break the deepest law of the small world. Here is a way to picture it. Imagine a tiny ball trembling at the bottom of a bowl. Every other ball in the world, cooled enough, would finally settle and lie still. This one cannot. Some invisible hand keeps flicking it, gently, endlessly, so it never quite stops shivering. That invisible hand is the uncertainty rule, and it never lets go no matter how cold the room gets. This is not a small curiosity. It is everywhere, and it holds up the world in ways you never see. That restless hum is part of why solids do not simply freeze into perfect, crushed stillness and collapse. The jitter keeps the atoms alive, always trembling, always holding their space even in the deepest cold that exists anywhere. Some substances take this to a wild extreme. Cool a certain lightweight material down near absolute zero, and its atoms are jittering so much from this leftover energy that the whole thing refuses to freeze solid at all. It stays liquid, flowing and creeping, when every other rule says it should have turned to ice. The trembling that will not stop keeps it forever fluid. So the electron in every atom is never truly at rest. It reached the bottom floor, the lowest state allowed, and there it hums forever, held by the same rule that keeps it from falling into the nucleus in the first place. It cannot fall lower. It cannot stop moving. It is locked into a gentle, eternal dance around the center, and nothing in the universe, not even perfect cold, can still it. That endless motion is the heartbeat of matter. But so far, we have watched only a single electron, alone with its nucleus. Real atoms are crowded places packed with many electrons at once, and when you try to stuff all of them onto that same comfortable ground floor, something forbids it. A brand new rule that will build the entire world of chemistry, one strange step at a time. Forget the marble, forget the little planet whipping around its sun. The picture of the electron as a tiny ball on a track has held on in your mind this whole time, and now it has to go for good. The electron in its ground state is spread out. It is smeared across the whole space around the nucleus, a soft glowing haze with no sharp edge and no single home. Scientists call it the electron cloud, and the name is honest. The electron is not at a place. It is a place, a fuzzy region of maybe, wrapped around the center. Think of a fan blade spinning so fast you can no longer see the blade. You see a solid disk, a blur that fills the whole circle at once. You could not point to where the blade is because in a sense it is everywhere in that disk. The electron is stranger still. It is a blur before it ever moves, a smear of pure possibility hanging around the nucleus. Here is what that really means. If you reach into the atom and try to find the electron, you might catch it here, near the center. Try again on a fresh atom, and you might catch it out at the edge. Again, and it is somewhere else entirely. The electron does not have one spot. It has a spread of odds, thicker in some places, thinner in others, filling the whole cloud. The cloud is densest close to the nucleus and fades as you move outward, like fog that is thick near the ground and thins into nothing as it rises. Where the cloud is thick, your odds of catching the electron are high. Where it is thin, your odds drop. But the electron itself is not sitting at any one of those spots waiting. It is all of them at once, until the moment you look. This is the deepest strangeness of the small world. Down here, things do not have sharp positions. They have clouds of possibility. The electron is a haze of where it might be, and only when something interacts with it does it snap to a single place, chosen by chance from all its options. So the atom is not a solar system at all. It is a dense little nucleus wrapped in a soft ball of blur, a haze of electron humming and shimmering with that restless energy it can never lose. The empty space we talked about at the very start is filled, gently, by this cloud of maybe. And this finally fully explains why the electron cannot crash. A marble can fall to a point, a cloud cannot. There is no single piece of the electron sitting at a single spot ready to drop straight down. The electron is smeared across a whole region, and you cannot make a smear fall into a point. It has no one place to fall from. The death spiral needed a ball on a track. Take away the ball, replace it with a cloud, and the spiral has nothing to grab. The whole disaster was built on a picture that was simply wrong. But this cloud hides a twist so strange it stopped scientists cold when they first saw it. Look closely at where the cloud is thickest, where the electron is most likely to be found, and you land in the last place you would ever expect. Right at the dead center. Right on the nucleus itself. Here is a fact that sounds like it should break everything we just built. In the ground state, the place where the electron is most likely to be found is the exact center of the atom, the nucleus, the one spot we spent 7 chapters saying it could never reach. At first, this seems like a flat contradiction. We said the electron cannot fall into the center. Now the math says the center is its favorite spot, the single point where the cloud is thickest and the odds are highest. How can both be true? The answer is a beautiful trick of counting, and once you see it, the whole atom clicks into focus. Yes, the cloud is densest right at the center. If you compare the exact center point to any other exact point out in the cloud, the center wins. The electron is more likely to be found right there than at any other single spot. But think about how much room there is at the center versus how much room there is further out. The center is one tiny point. A shell of space out at the edge of the cloud, even though it is thinner, wraps all the way around the atom in a giant sphere. There is vastly more room out there than there is at the single point in the middle. Picture a city where the very center square has the most people packed per step of ground. It is the most crowded spot in town, but the outer ring of the city, though less crowded per step, stretches around the whole edge and covers far more total ground. Count heads, and most people live in the wide outer ring, even though the tightest crush is downtown. The electron works the same way. The center is the most crowded single point. But when you add up all the room in the wide shells further out, the electron spends most of its time out there, in the roomy zone, not jammed at the center. The favorite point and the favorite region are two different things. So the electron does visit the center, it even favors that exact point above all others. But it does not stay there, and it does not pile up there, because a single point holds almost no room, and the electron is a cloud that fills a whole volume. This is why the earlier picture still holds. The electron does not fall into the nucleus and stop, because it is spread across a huge region and only dips through the center as part of its blur. It passes through, thickest right there, yet never trapped there, always spread back out across the roomy space around it. And here is the part that should unsettle you. Since the electron cloud is thickest at the center, the electron really is, in a sense, sitting on top of the nucleus a good deal of the time. It overlaps the very thing it is supposedly forbidden to reach. The forbidding was never about staying away. It was about never collapsing down to that point and stopping. So a new question rises up. If the electron is already there, already blurred right through the nucleus, already overlapping it constantly, then what actually stops it from just staying? Why does it not settle into that favorite center point and finally, quietly, end the whole story? The electron passes through the center. It even favors that spot. So why does it not simply stop there, sink in, and be done? Because stopping is the one thing it cannot do. And to see why, you have to understand what falling really means. When a ball falls, it starts somewhere high, with a position you can point to, and it drops to a spot lower down. Falling needs a starting place and a finish place. It needs the thing that falls to be somewhere definite so it can move from here to there. The electron cloud has no definite somewhere. It is smeared across the whole atom at once, a haze with no single position. And you cannot make a haze fall, because there is no one point where it sits to begin the drop. Falling is a thing that happens to objects with a location. The electron, spread into a cloud, has no location to fall from. Try to force it. Try to gather the whole cloud down onto the center point, to make it a tiny speck sitting on the nucleus. The instant you squeeze the cloud that small, Heisenberg's rule wakes up with full fury. A cloud crushed to a point means a position pinned down perfectly, and a perfectly pinned position means a wild, exploding motion. The energy needed to hold the electron there would rocket toward the impossible. So the electron faces a strange bargain. It can pass through the center as part of a wide, spread-out cloud, cheaply, calmly, costing almost nothing. Or it can try to collapse down and truly sit at the center as a tiny point, at a cost of energy so enormous the atom could never pay it. The first is easy. The second is forbidden by the price. Nature always takes the cheap path, so the electron stays spread out, dipping through the center as a thick part of its cloud, refusing to ever crush itself down into the point that would let it stop. It has its cake and skips the bill. It gets to be densest at the centre, without ever paying the price of staying there. Picture fog rolling over a valley. The fog is thickest in the low centre of the valley, pooling there. But the fog is not falling into a single spot and vanishing. It is spread across the whole valley, thick in the middle, thin at the edges, sitting there as a spread out thing. You cannot point to where the fog is, and you cannot make it drop into a point because it is a haze, not a stone. The electron is that fog, pooled thick at the centre of the atom, spread thin toward the edges, never collapsing, never falling, never stopping. It reached its lowest state long ago and settled into this permanent spread, the cheapest, calmest shape it is allowed to have. This is the full answer to the question we started with. The electron cannot fall into the nucleus because it is a cloud, and a cloud cannot fall to a point without paying an impossible price in energy. The mystery that terrified the greatest physicists on Earth comes down to this quiet truth about what the electron truly is. For years, all of this lived in scattered pieces, guesses and rules and clever tricks. Then one man wrote a single equation that tied every piece together, and out of it the whole atom appeared, cloud and all. In the winter of 1926, an Austrian physicist named Erwin Schrödinger went away to a mountain cabin and came back with an equation that would change how we understand everything. Up to this point, the atom had been explained with a patchwork. De Broglie said the electron was a wave. Heisenberg said its position was fuzzy. Bohr said the orbits came in steps. Each idea was right in its own way, but they were scattered pieces, none of them tied into a single clean whole. Schrödinger tied them together. His equation describes the electron wave and how it behaves inside the atom. You feed in the pull of the nucleus, and the equation tells you every possible shape the electron wave can take, and how much energy each shape carries. One equation, and the entire structure of the atom falls out of it. What came out was breathtaking. The equation did not just handle hydrogen, the way Bohr's staircase did before it stumbled on everything harder. Schrödinger's equation described the electron clouds directly, their shapes, their sizes, their energies. It drew the whole fuzzy blur we have been talking about straight from the math, and it worked. The energy levels it predicted matched the real glowing colours of hydrogen, the same colours Bohr had explained, but now with a deep reason underneath instead of a rule pulled from the air. The staircase was real, and here at last was the machine that built it. Better still, the equation explained the finer details that had wrecked Bohr's model. Those extra lines that split off, the ones the old staircase could not touch, started to fall into place. The shapes of the clouds, why some are round balls and others are shaped like dumbbells or clover leaves, all of it poured out of this one piece of math. Here is the strange heart of it. The equation does not tell you where the electron is. It tells you the shape of the cloud, the map of odds, where the electron is likely and unlikely to be found. Schrödinger's math gives you the fog, not the stone. It predicts the haze of possibility directly, because that haze is what the electron truly is. Think of the equation as a master recipe for the atom. Give it the nucleus and its pull, and it hands back every allowed shape the electron can take, ranked by energy, from the calm low ground state up through the wild higher ones. Every atom, every cloud, every energy step, all of it, written in the language of this one rule. Scientists could now calculate atoms they had never even measured. They could predict how atoms would bond, what shapes molecules would take, why the periodic table lines up the way it does. The whole of chemistry, the whole reason different elements behave differently, traces back to the cloud shapes this equation draws. It was one of the greatest achievements in the history of human thought, a single equation describing the deepest structure of matter still used today in every chemistry lab and physics department on Earth. Schrödinger won the Nobel Prize, and his equation became one of the pillars the modern world stands on. But buried inside this equation was a surprise that even Schrödinger found astonishing. When he solved it, whole numbers came marching out on their own, clean and counted, with no one having put them there. The atom, it turned out, counts. When Schrödinger solved his equation for the atom, something appeared in the answer that nobody had placed there by hand. Whole numbers, clean, counted, exact. 1, 2, 3. They rose up out of the math on their own, and they decided the entire structure of the atom. To feel how strange this is, think about most of the world, which does not come in whole numbers at all. You can pour any amount of water into a glass, a little more, a little less, smoothly, with no jumps. You can drive at any speed you like. Nature usually flows in smooth steps, allowing every value in between. But the atom refuses. It counts. The energy an electron can have is not smooth. It comes only in certain allowed amounts, set by whole numbers, with forbidden gaps between them. The electron can sit at level 1 or level 2 or level 3. It can never sit at level 2.5. The in-between values simply do not exist for it. This is where Bohr's staircase came from, revealed at last. Bohr had guessed the steps were there and could not say why. Schrödinger's equation showed exactly why. The whole numbers fall out of the math because of the same rule as the guitar string. A wave trapped in a space can only fit in whole, clean patterns, 1 hump, 2 humps, 3, never 2.5. The whole numbers are the count of how the wave fits. Remember the guitar string, pluck it, and it rings at certain clear notes and no others, because only certain whole numbered wave shapes fit between its fixed ends. The electron wave, trapped by the pull of the nucleus, obeys the very same law. It can only take shapes that fit cleanly, and those clean fits are counted by whole numbers. The counting is built into what a trapped wave is. These whole numbers do far more than set energy. They set the shape of every electron cloud, the size of every orbit, the way electrons stack up inside bigger atoms. They are the hidden code that builds the whole periodic table. Every element on that famous chart is different, because its electrons fill up these counted levels in a different pattern. So the reason gold is gold, and oxygen is oxygen, and iron is iron, comes down to these whole numbers marching out of Schrödinger's equation. Each element has its own count of electrons, filling the counted levels in its own way, giving it its own personality, its own colour, its own way of bonding with the world. This is one of the most profound facts in all of science. The universe, at its smallest scale, is built on counting. The smooth-flowing world you see all around you is made of tiny pieces that come only in whole, exact steps. Zoom in far enough on anything, and you find the atom counting 1, 2, 3, allowing these values and forbidding all the ones between. The electron then lives its whole life inside these counted steps, resting at the bottom one, forbidden from any place between. It is a deeply orderly picture, clean and reliable, the same in every atom everywhere. And yet, for all this order, nature keeps one shocking exception up its sleeve. In certain special atoms, the rule we have followed actually breaks. The nucleus reaches out, and it does the impossible. It swallows one of its own electrons whole. Everything so far has said the same thing. The electron cannot fall into the nucleus. It is blocked, held out, forbidden to reach the centre and stay. But nature loves an exception, and here is a stunning one. In certain atoms, the nucleus really does swallow an electron. The forbidden thing happens. It sounds like everything we built just collapsed. It does not. And understanding why reveals something even deeper about the rule we have been chasing. Some nuclei are unstable. They are packed wrong inside, carrying a poor balance of the tiny pieces that make them up. These lopsided nuclei are restless, straining, looking for any way to shift into a more comfortable arrangement. They are like a stack of blocks leaning too far to one side, ready to topple toward balance the moment they get a chance. For certain of these strained nuclei, there is a way out that involves the electron. If the nucleus could just grab one of the electrons from the cloud around it and pull it inside, the whole atom would settle into a calmer, more balanced state. So that is exactly what it does. The nucleus reaches into its own electron cloud and captures an electron, taking it in. Remember, the electron cloud is thickest right at the centre, which means the electron spends a good part of its time overlapping the nucleus, blurred right through it, so the nucleus does not have to reach far at all. The electron is already there, passing through, again and again. The nucleus just has to catch it during one of those passes. This is why the earlier rule still holds true. The electron was never truly banned from the centre. It visits constantly, thickest right there. What it cannot do on its own is collapse and stop. But if the nucleus is unstable and hungry, it can seize the electron during one of those centre visits and pull it in for good. So the electron falls into the nucleus after all, but only with the nucleus actively grabbing it, and only when doing so lets the nucleus reach a calmer state. It is a rare event, happening in special unstable atoms, one electron caught out of the whole, restless cloud. This process has a plain name. Scientists call it electron capture, and it is real, measured, confirmed in labs and running quietly inside certain atoms in your own body and all around you. Some of the atoms that make up the world are doing this right now, catching their own electrons, settling into balance. Here is the beautiful lesson hidden inside the exception. The reason the electron normally stays out is not a hard wall, some barrier it physically cannot cross. It is about energy and balance. As long as the atom is stable, keeping the electron out in its cloud is the low energy, comfortable arrangement, so the electron stays spread out. But when swallowing, the electron would leave the nucleus calmer, the whole balance flips, and in the electron goes. So the great rule bends when the energy says it should. The electron is held out by a truce, and a truce can be renegotiated when the numbers change, and when the nucleus does swallow that electron, something extraordinary happens inside. The electron and a piece of the nucleus meet, merge, and transform into something new, a tiny act of alchemy, deep at the heart of the atom. Look inside the nucleus at the moment of capture, and you witness one of the strangest transformations in nature. An electron vanishes into a proton, and out of the merger comes something entirely new. First, meet the players. A nucleus is built from two kinds of pieces: protons, which carry a positive charge, and neutrons, which carry no charge at all. The balance between these two kinds of pieces is what makes a nucleus stable or unstable. Too many protons for its liking, and the nucleus grows restless, straining for a fix. Here is the fix that electron capture provides. The nucleus pulls in a negative electron. That electron drives straight into one of the protons, and when a proton and an electron merge like this, they become a neutron. The positive proton and the negative electron combine, their charges cancel, and what is left is a neutral neutron. Watch what that does to the nucleus. A moment ago it had one too many protons leaning out of balance. Now one of those protons has turned into a neutron. The count has shifted. The nucleus has traded a proton for a neutron, and suddenly it sits in a calmer, more balanced state. The strain eases. The atom relaxes. This is real alchemy. The ancient dream of turning one element into another, happening quietly inside these atoms. Because the number of protons is what decides which element an atom is. Changing a proton into a neutron changes the element itself. The atom becomes a different substance entirely, a neighbour on the periodic table, born from swallowing its own electron. A comparison helps here. Picture a seesaw with too much weight on the proton side, tipped hard and straining. Electron capture reaches over, lifts a weight off the heavy side and sets it down on the other. The seesaw swings toward level. The nucleus does the same, moving a unit from the crowded side to the emptier one, finding its balance. There is one more piece to the story. When the proton and electron merge into a neutron, a tiny ghost of a particle shoots away at the speed of light. Scientists call it a neutrino. It is almost nothing, carrying no charge and barely any substance, and it passes through matter as if the matter were not even there. Trillions of them are streaming through your body this very second, from the sun and from atoms all around you, and you never feel a single one. That fleeing neutrino carries off a little of the leftover energy, balancing the books, making sure the transformation adds up perfectly. It is the receipt for the whole transaction, flying away into space, proof that the merger obeyed the deep laws of nature. So the electron that seemed forbidden to fall does sometimes fall, and when it does not simply crash and sit there. It merges, transforms, and helps turn one element into another, releasing a ghostly messenger as it goes. The forbidden collapse becomes a quiet act of creation. This tells us something important about the rule we have chased all along. The electron staying out of the nucleus was never a brick wall. It was a matter of which arrangement holds less energy. And that changes how you should picture the whole barrier keeping the electron out. It was never a wall at all. It has been tempting to picture a wall, a hard barrier around the nucleus keeping the electron out, blocking it from the centre like a fence blocks a trespasser. That picture is easy, and it is wrong. There is no wall. What holds the electron out is not a barrier. It is a slope, a matter of energy and odds, of which path costs more and which costs less. and once you swap the wall for a slope, the whole atom finally makes sense. Think about what a wall means. A wall is a place the electron physically cannot go, a hard line it slams into and cannot cross. But we have already seen the electron pass right through the centre, thickest of all at the very point it supposedly cannot reach. There is no wall there. The electron goes wherever it likes. What it will not do is stay crushed at the centre, because staying there costs a fortune in energy. So picture a slope instead. Imagine a wide, smooth bowl. A ball can roll anywhere inside it, high on the sides or low in the middle. Nothing blocks it. But it takes energy to climb the sides, and the ball naturally settles toward the low, easy part where the cost is least. No wall stops the ball from climbing. It just costs more to be up high, so the ball rests low. The electron lives on a slope like that, shaped by energy. Down at the centre, crushing itself to a point would cost an enormous amount of energy, because of Heisenberg's rule and the exploding motion of confinement. Far out from the nucleus, drifting free would also cost energy, because the pull of the nucleus wants to hold it close. Between those two costly extremes sits a comfortable low spot, and the electron settles there, in the ground state, where the total cost is least. Nothing forbids the electron from the centre. Nothing forbids it from far away. It simply rests where the energy is lowest, the same way water pools in the bottom of a valley, not because walls trap it there, but because that is the lowest, cheapest place to be. This is why electron capture can happen at all. If the barrier were a real wall, nothing could ever get through, but since it is a slope shaped by energy, the balance can shift. Change the situation, make it cheaper for the electron to be inside the nucleus, and the slope tilts, and in it goes. A wall could never bend like that. A slope of energy bends whenever the numbers change. So the deep truth of this whole story is about energy and probability, not barriers and blocks. The electron is a cloud of odds, resting in the lowest energy shape it can find, spending most of its time where the cost is least. It stays out of the crushed centre because staying there is expensive, and it stays close to the nucleus because drifting away is expensive too. The atom is a landscape of energy, and the electron is a cloud that pools in the valleys. That is the real picture, the one that finally holds together with no contradictions. But now bring in the crowd. Real atoms hold many electrons at once, and when you try to pool all of them into the same low valley, the same comfortable ground floor, a brand new law slams down and forbids it. One of the strangest rules in all of physics. Everything so far watched a single electron. One nucleus, one cloud pooling in the lowest valley. But most atoms are crowded. Oxygen carries 8 electrons. Iron carries 26. Gold carries 79. And here a new puzzle appears that nearly broke physics all over again. If the ground state is the lowest, cheapest, most comfortable place for an electron, then every electron should want it. In an atom with many electrons, they should all pile into that same bottom valley, stacking up together in the lowest state, since that is where the energy is least. All of them, crammed onto the ground floor. If that happened, the universe would be a disaster. Every atom would collapse into the same tiny, dense arrangement. Every element would behave almost the same, all their electrons jammed into the identical lowest state. There would be no rich variety of chemistry, no reason for gold to differ from oxygen, no periodic table, no life. Everything would blur into sameness. Look around. That is not the world we have. Elements are wildly different. Chemistry is rich and varied. Something stops all the electrons from piling into the ground floor. Something keeps them apart. That something came from a sharp, exacting physicist named Wolfgang Pauli, who in 1925 wrote down a rule so strict it sounds almost like a decree. No 2 electrons in an atom can be in the exact same state at the same time. Each electron must have its own unique arrangement. They are forbidden from copying each other. Scientists call this the exclusion principle, and it is one of the most powerful rules in all of nature. It means the ground floor of the atom has limited seats. Once those seats are filled, no more electrons are allowed in. The next electrons are forced up to the next level, and when that fills, up to the level after that. Picture a theatre with assigned seats, and a strict usher. Everyone would love to sit in the front row, closest to the stage, the best spot in the house. But each seat holds only one person, and once the front row is full, the usher sends the next arrivals to the second row, then the third. Nobody gets to double up. The theatre fills from the front back, row by row, because no two people can share a seat. Electrons fill an atom the very same way. The lowest level takes its allowed few and then it is full. The next electrons are pushed up to the second level. Fill that, and the rest go higher still. The atom fills from the bottom up, level by level, because Pauli's rule forbids any two electrons from sharing the same exact state. This one rule builds the entire structure of every atom heavier than hydrogen. It is the reason electrons spread out into layers instead of collapsing into one shared pile. It is the reason atoms have an outer edge, an outermost layer of electrons that reaches out to touch the world. And that outer layer is what does all the chemistry. So Pauli's rule is quietly responsible for the whole variety of matter. Without it, sameness. With it, the rich layered structure that makes every element its own thing. And those layers have a name and a pattern, one you've seen hanging on the wall of every science classroom on Earth. Those filled levels have a name. Scientists call them shells, and the way electrons stack into these shells builds the most famous chart in all of science. The periodic table, that grid of squares on the classroom wall, is a map of how electrons fill their shells. Here is how it works. Electrons fill the atom from the bottom up, obeying Pauli's rule one level at a time. The innermost shell, closest to the nucleus, holds only a small number of electrons before it is full. Fill it, and the next electrons move out to the second shell, which holds more. Fill that, and they move to the third, and so on outward. Each element has its own number of electrons, so each element fills these shells to a different point. And the electrons in the outermost shell, the ones on the very edge, are the ones that reach out and grab onto other atoms. Those outer electrons do all the bonding, all the chemistry, all the joining that builds molecules. This is the secret the periodic table reveals. Elements are arranged so that ones with similar outer shells line up in the same column. Look down any column, and every element in it has the same number of electrons in its outer shell. That shared outer arrangement is why they behave alike, why they bond in similar ways, why they belong together. Take the column on the far right, the ones with completely full outer shells. A full outer shell is deeply content. It has no need to grab any more electrons and no urge to give any away. So these elements barely react with anything. They float through the world aloof and alone. These are the gases that fill glowing signs and lift party balloons, calm and unbothered, because their shells are already full. Now look at the opposite case. Elements with just one lonely electron in their outer shell. That single electron is loosely held, eager to leave, so these elements are wildly reactive, desperate to hand off that spare electron. Some of them burst into flame the moment they touch water. Their whole violent personality comes from one electron sitting alone in an outer shell. A comparison makes it clear. Think of each shell as a row of seats that fills up completely before the next row starts. An atom with a full outer row is satisfied and still. An atom with one empty seat is restless, reaching out to grab an electron and complete itself. An atom with one extra electron past a full row is eager to give it away. All of chemistry, every reaction, every bond is atoms trading and sharing electrons to reach that satisfied full shell state. So the entire richness of the material world, every substance, every reaction, every molecule in your body, comes down to how electrons stack into shells and how the outer ones behave. The periodic table is not a random chart to memorize. It is the direct picture of electrons filling their levels, arranged so the patterns line up in plain sight, and all of it rests on Pauli's rule, forcing electrons to spread into shells instead of piling together. Take away that rule, and the table collapses into sameness. Keep it, and you get the whole beautiful variety of matter. But why does the rule exist at all? Why can no two electrons share a state? The answer lies in a bizarre hidden property of the electron, something with a misleading name and no equal in the world you can see. Pauli's rule keeps electrons apart, but it leaves a haunting question. Why? What is it about electrons that forbids any two of them from sharing a state? The answer is a strange inner property with a misleading name. Scientists call it spin. The name makes you picture a tiny ball whirling like a top, turning on its axis. Erase that picture. The electron is not really spinning like a top. Spin is a deep inner property it carries, something with no true match in the everyday world, and the name is just a leftover from when scientists first guessed wrong about what it was. Here is what matters. Every electron carries this property called spin, and it comes in exactly two flavors. Scientists label them spin up and spin down. An electron is always one or the other. There is no in between, no third option, just up or down. Now bring back Pauli's rule. Two electrons cannot be in the exact same state, but spin gives each electron one more feature that can differ. So two electrons can share the same shell, the same energy level, the same cloud shape, as long as one is spin up and the other is spin down. Their spins make them different, so the rule is satisfied. They are allowed to pair, but only two. Once a spot holds one spin-up electron and one spin-down electron, it is full. A third electron would have to match one of the two already there in every way, including spin, and that is forbidden. So it is pushed elsewhere. This is exactly why each level holds the number it does. Each spot takes two electrons, one of each spin, and no more. This is where the theatre seats came from earlier. Each seat actually holds two, a spin up and a spin down, sitting together. Fill both, and the seat is taken. The next electron must find another seat entirely. Spin is the reason electrons pair up 2 by 2 as they fill the atom. Spin does something even stranger. It makes electrons actively avoid each other in a way that goes beyond simple charge. Electrons with the same spin refuse to be in the same place, twisting away from one another as if repelled by a force with no name. This deep avoidance is woven into what electrons are, a built-in standoffishness that keeps them spread apart. Picture a strange dance where no two dancers with the same coloured shirt are ever allowed to stand on the same square. Red shirts and blue shirts can share a square, one of each, but two reds can never overlap, and two blues can never overlap. They are forced to spread across the floor, always keeping their distance from their own kind. Electrons dance exactly like that. Spin up avoiding spin up, spin down avoiding spin down, spreading themselves across the atom. This built-in avoidance, this refusal of identical electrons to pile together, is one of the most powerful forces shaping matter. It is the deep root of Pauli's rule, the reason electrons stack into shells, the reason the periodic table exists, the reason you are made of varied structured stuff instead of a uniform blob. And this same shy, stubborn property does something almost beyond belief on the grandest scale. That tiny refusal of electrons to share space is strong enough, when you gather enough of it, to hold up an entire dead star against the crushing weight of its own gravity. Take everything you have learned about electrons refusing to be crushed together and now blow it up to the size of a star. Because that same tiny stubbornness, multiplied across unimaginable numbers, holds up one of the strangest objects in the universe, a dead star called a white dwarf. A star lives by burning. Deep in its core, it fuses tiny nuclei together and pours out energy, and that outward flood of energy pushes back against the star's own gravity, holding it up, keeping it puffed out and shining. For billions of years, the star balances there, burning against the crush of its own weight, but the fuel runs out. When a star like our Sun finally burns through its supply, the outward push dies and gravity takes over. Nothing holds the star up anymore. It begins to collapse, falling inward under its own crushing weight, squeezing smaller and smaller, denser and denser. You would think nothing could stop it. Gravity is relentless, and there is a lot of star pressing down. The collapse should crush the whole thing to a point, but it stops. Something catches the falling star and holds it, freezing it at a size roughly like our own planet Earth. A whole star's worth of matter, squeezed down to a ball the size of a world. What stops the collapse is the very rule we just met. As gravity crushes the star's electrons closer and closer together, they begin to refuse. Pauli's rule forbids them from piling into the same state, and their built-in avoidance, their stubborn refusal to share space, pushes back against the crush. The tighter gravity squeezes, the harder the electrons shove outward, exactly like that caged electron thrashing in its shrinking box. This outward shove has a name. Scientists call it degeneracy pressure, and it is not made of heat or burning or any ordinary force. It comes purely from electrons refusing to be crushed into the same state. It is Pauli's rule, made strong enough to hold up a star. The numbers are staggering. A white dwarf packs the mass of an entire star into the size of a planet. One spoonful of white dwarf matter would weigh about as much as a truck, maybe several tons, crushed into a single scoop. The whole star is squeezed to that unthinkable density, and only the stubbornness of its electrons keeps it from collapsing further. Think about what that means. The same rule that keeps the electron in your fingertip from crashing into its nucleus, the same shy refusal of electrons to share a state scaled up across a dying star, is strong enough to defy the gravity of an entire sun. The tiny standoff inside every atom becomes a mighty wall holding up a corpse of a star. Our own sun will end this way. In billions of years it will burn out, collapse and settle into a white dwarf, held up forever by electrons refusing to be crushed. It will sit there, dense and slowly cooling, a diamond-hard ember the size of the Earth, propped up by the same rule woven into every atom of your body right now. But even this mighty force has a limit. Pile on enough weight, enough gravity, and the electrons finally lose, and when they lose, something far more violent and far stranger is born. The stubbornness of electrons can hold up a dead star. But it is not unbreakable. Pile on enough mass, enough crushing gravity, and even that mighty refusal finally gives way, and when it does, the collapse that follows is one of the most violent events in the universe. Here is the limit. The electron pressure holding up a white dwarf can only support so much weight. If a white dwarf is light enough, it holds forever. But if enough mass presses down, if the star is heavy enough, gravity grows stronger than the electrons can resist. There is a hard ceiling, a maximum weight the electron stubbornness can bear, and beyond it, they lose. When gravity wins, the collapse is sudden and catastrophic. The electrons, crushed beyond their limit, can no longer hold their ground. Gravity slams the star inward, and now nothing stops it. The whole thing falls, faster and faster, matter crushing down in a fraction of a second. And here is where it connects back to everything we learned. As the star collapses, gravity forces the electrons and protons together with unstoppable power. Crushed close enough, they do the very thing from before. Each electron is driven into a proton, and together they become a neutron. Electron capture, but happening everywhere at once, across the entire star, in a single violent instant. Every proton swallows an electron. Every pairing becomes a neutron. The whole star, in a heartbeat, turns almost entirely into neutrons packed shoulder to shoulder. What was a star of ordinary matter becomes a single, unthinkably dense ball of neutrons. A neutron star is born. The density is beyond anything you can picture. A neutron star squeezes more mass than our entire sun into a ball only about a dozen miles across, small enough to sit inside a city. One sugar cube of neutron star matter would weigh about as much as a mountain, maybe 1 billion tons crushed into that tiny space. It is the densest kind of matter that can still hold itself up at all. What holds it up now? The neutrons themselves. Neutrons obey the same Pauli rule as electrons. They too refuse to share a state, and they too push back with their own degeneracy pressure. So the collapse halts again, this time held by crushed neutrons instead of crushed electrons, at a density thousands of times greater than the white dwarf that failed. Picture the whole grand chain. In an atom, electron stubbornness keeps a single electron from crashing into a single nucleus. In a white dwarf, that same stubbornness holds up a whole dead star. Push past its limit, and the electrons are crushed into the protons, the star turns to neutrons, and now neutron stubbornness holds the line instead. The same deep rule, fighting gravity at every scale, giving way and then digging in again. A neutron star spins fast and burns with fierce fields, a lighthouse of the cosmos, sweeping beams across space. It is the crushed corpse of a giant star, held up by nothing but particles refusing to share their state, the grandest version of the tiny standoff inside your atoms. But there is one more level of crushing, one final weight so great that even the neutrons lose. And when that happens, every rule we have followed surrenders at last. Neutron stubbornness holds up a neutron star. But nature has one more weight to drop, one final crush so total that even the neutrons give way, and when they do, every rule of resistance we have followed surrenders completely. You get a black hole. Here is the last limit. Just as electron pressure could only hold so much before failing, neutron pressure has its own ceiling. Pile enough mass onto a neutron star, press it with enough gravity, and even the neutrons, refusing as hard as they can to share their state, are overwhelmed. Their stubbornness, mighty as it is not infinite. Gravity given enough weight beats it, and this time there is no next line of defense. When electrons failed, neutrons caught the fall, but when neutrons fail, nothing waits below them to catch the star. Every source of resistance is exhausted. The collapse that begins now does not stop at any size at all. The star falls inward, past the density of a neutron star, past every limit, crushing down with nothing to halt it. The matter squeezes smaller and smaller toward a point of endless density, a place where our understanding of space and matter breaks down entirely. Gravity has won absolutely, and the collapse runs all the way to the end. Around this crushed remnant forms a boundary, a line in space that changes everything. Cross it, and the pull is so strong that not even light can climb back out. This is where the black hole gets its name. Light itself, the fastest thing in the universe, falls in and cannot escape. From outside, all you see is a perfect darkness, a hole where a star used to be. The pull is total. Anything that crosses that boundary, light, matter, anything at all, falls inward and never returns. The escape that electrons and neutrons fought so hard to provide, the outward push that held up dead stars, is gone. Gravity reigns with no rival left. Think of the whole journey we have taken. In an atom, the electron cannot fall into the nucleus, held out by its own nature. In a white dwarf, electrons hold up a star. In a neutron star, neutrons hold the line when electrons fail. And here, at the black hole, even that final resistance collapses, and matter falls all the way in, at last, with nothing to stop it. The black hole is the one place in the universe where the great rule finally, fully loses. Everywhere else, some stubbornness holds matter apart and gives it size. Here, that stubbornness is crushed out of existence, and matter falls into a point we cannot even describe with our current laws. It is the ultimate failure of the standoff that keeps your own atoms from collapsing. And yet, this makes the everyday miracle even more striking. The same gravity that crushes stars into black holes is pulling on every atom in your body right now. It is far too weak to win at your scale, easily held off by the stubbornness of your electrons. It takes an entire collapsing star to overwhelm what a single atom shrugs off without effort. So the rule that keeps the electron out of the nucleus is strong beyond belief. It takes the death of a giant star to break it. And this same rule hides a final surprise. One that shows just how delicately the size of every atom hangs on the exact nature of the electron itself. Here is a strange experiment nature lets us run. The electron has a heavier cousin, a particle almost exactly like it in every way but one. It is much heavier. Swap the electron in an atom for this heavy cousin, and the whole atom shrinks dramatically. This tells us something profound about why atoms are the size they are. The cousin is called a muon. In every important way, a muon is a copy of the electron. Same negative charge, same behavior, same rules. The one difference is weight. A muon is about 200 times heavier than an electron. That single change, more weight, transforms the entire atom. Remember why the atom has size in the first place. The electron cannot be crushed to the center, because confining it forces its energy to explode, by Heisenberg's rule. But that explosion of energy depends on the particle's weight. A lighter particle fights confinement harder, spreading into a wide cloud. A heavier particle fights less, so it can be squeezed into a much smaller space before its energy climbs too high. The muon is heavy, so it does not resist confinement nearly as fiercely as the electron. It settles into a cloud far closer to the nucleus, a much tighter orbit. Swap in a muon, and the atom it forms is about 200 times smaller than the ordinary version. The same nucleus, but wrapped in a cloud shrunk down enormously, all because the particle circling it weighs more. This is stunning proof of everything we have said. The size of the atom is set by the balance between the pull of the nucleus and the outward push of confinement. Change the weight of the particle, and you change that balance, and the atom changes size to match. The width of an atom is written directly into the nature of the electron itself. A comparison helps. Imagine two balloons in a strong wind. one light and one heavy. The light balloon gets blown far out, held at a distance by the push of the air. The heavy balloon barely moves, sitting close and tight. The electron is the light balloon, blown out into a wide cloud. The muon is the heavy one, sitting tight and close. Same pull, different weight, wildly different size. These muon atoms are real. Scientists make them in labs and they behave exactly as predicted, shrunk down small. They are fragile and short-lived, because the muon does not last long before it decays away. But for the brief moment they exist, they prove the point perfectly. The atom is as big as it is only because the electron is as light as it is. Think about what this means for your world. If the electron were heavier, every atom would be smaller, and all of matter would be built to a different, tinier scale. The size of everything, your body, the ground, the air, traces back to the exact lightness of this one tiny particle. Make it heavier, and the whole world shrinks. So the electron's refusal to fall, and the size that refusal creates, hangs on the delicate fact of how light the electron is. Change that one number, and everything changes with it. And this brings us to the final, grandest truth of the whole story. This one strange rule, the reason the electron cannot fall, is quietly holding up your entire world, right now, in ways you feel every single second. We started with a lie your body tells you. Your hand feels solid, yet it is almost entirely empty space, a swarm of tiny nuclei wrapped in clouds of blur, held apart by a rule you could not see. Now, at the end, you can see it. And it turns out this one rule is holding up your entire world. Follow the whole chain back. The electron cannot fall into the nucleus because it is a cloud, a wave, a haze of possibility that cannot crush itself to a point without its energy exploding. Heisenberg's rule forbids the perfect stillness that falling would require, so the electron rests in its lowest state, spread out, humming forever, keeping the center open and the atom whole. That refusal to be crushed is why atoms have size, and because atoms have size, everything made of atoms has size. Your body, the chair beneath you, the ground under your feet, all of it takes up space only because electrons refuse to be pushed into a point. Take away that rule, and every atom collapses, and the whole world crushes down to nothing. Now feel the floor holding you up. Right now, you're not falling through your chair. Why not? The chair is mostly empty space, and so are you. By raw emptiness alone, you should sink straight through. But you do not, because the electrons in your body meet the electrons in the chair and neither set will be crushed into the other. They push back. That push is the solid feeling of the seat beneath you. Every solid thing you have ever touched is solid for this reason. Press your hand on a table and the table does not give because its electrons refuse to be squeezed into yours. The hardness of stone, the firmness of steel, the simple fact that you can hold a cup without your fingers passing through it, all of it is electrons standing their ground, refusing to share their space. Think of how far this reaches. The same rule that keeps one electron out of one nucleus builds the whole periodic table, gives every element its character, lets atoms bond into the endless variety of the material world. It holds up dead stars against their own gravity. It sets the size of everything that exists. One rule, echoing from the heart of a single atom, all the way up to the corpses of giant stars, and it is happening inside you at this very moment. Every atom in your body is holding this balance, silently, without rest. The electron clouds spread and humming, never falling, never crushing, keeping you whole. Trillions upon trillions of tiny standoffs, all holding at once, are the reason you have a shape, a size, a solid form to call your own. The physicists who first faced this puzzle thought the atom should die in a flash, that matter itself could not exist. They were staring at the deepest rule of reality without knowing it. The answer they found rewrote what solid means, what touch means, what you are made of. So the next time you knock on a table and feel it push back, remember what you are really feeling. Not wood. The fury of countless electrons, refusing to fall, refusing to be crushed, holding up your entire world with a rule woven into every speck of matter that has ever been. That quiet refusal is the reason for everything solid. It is the reason for you.